Welcome to my talk. Today I'm very excited to talk about ModelKeeper, a model manager to accelerate model training by repurposing the weights of previously trained models. It's a joint work with Yinwei, Harsha, and Mosharaf. In the past decade, we have seen a great leap in deep learning performance and adoptions. This leap was made possible by the hardware improvement, big data, and the advance in machine learning theory. These three drivers allow us to develop more powerful deep neural networks for various applications and tailor them to different resource settings and users. Now, this growing demand for more ML adoptions and better adoptions has led to the increasing number of training jobs because different model architectures, model sizes, and computations can often have different model accuracy. So unlike traditional big data analytics, ML development is often exploratory and collaborative across many developers. Thinking about developing face detection models for edge devices, due to the great variety of hardware and models, developers often start with training various model architectures to find the performance frontier for different systems and accuracy preferences. Indeed, Microsoft training cluster performs as many as 100 model exploration jobs for each application. Other than this model exploration, developers often train dozens of models to combine their predictions for better accuracy, like ensemble learning, and iterate this development for the new resource settings and users. So even the development of a single application can lead to training hundreds of models. Now, with this increasing number of applications, large clusters often run thousands of training jobs every day, leading to a large pool of trained models. But most of these models remain untouched beyond their own job. As model training is often expensive, can we repurpose these models to benefit the training of new jobs and even across developers? In fact, the model is often a graph of tensors. Each tensor associates with an operation and tensor weights, like the full connection layers with different shapes of weight values, and training searches for the best weight values for that architecture. Intuitively, instead of training from scratch, often with randomly initialized model weights, referring to a well-trained model with similar architectures should offer a better initialization. It's similar to transfer learning, but further extends this transfer across different architectures. Let me show you an example. Here, this figure shows the convergence of training an image classification model, ResNet 101, in two different ways. The x-axis reports the number of training epochs on the CIFAR dataset, and the black line reports the setting of training from scratch, while the orange line copies the weights of a previously trained ResNet 50 model to Warmup training. We are seeing that this Warmup can save the amount of training execution needed without hurting model accuracy. This implies an exciting opportunity to benefit the training of new jobs with little overhead. It's very important for practical deployment because the overhead of sophisticated solutions like knowledge distillation is often too expensive when serving thousands of daily jobs. Due to the large number of jobs, we found large clusters often contain jobs with similar model architectures. Although we now have some model zones available, like the pre-trained models in the Hugging Face model zone, we want an automated training warm-up because jobs are submitted from users with varying expertise, and jobs can often have different model architectures. So it's impractical for us to manually search for which model to repurpose and then manually transform its model weights every time. So we introduced ModelKeeper as a cluster-level model service to automate training warm-up in a few lines of code change. Here, developers submit their warm-up request to the coordinator. Then, ModelKeeper manages a zoo of trained models at runtime, like the Hugging Face model zoom, and transforms a model's weights to the weight matrix of that query model of the user to warm up its training. All these operations take place before training starts, so the rest of training remains the same. In designing ModelKeeper, we want to achieve beneficial weight transformation as much as possible. Actually, the effectiveness of this warmup is determined by the architectural similarity and the accuracy of the model to be repurposed. Let's call it the parent model. A high similarity implies a larger number of transformable weights, but a higher accuracy implies better weights to transform. However, models are often heterogeneous in terms of their model architectures and accuracy, so it's quite difficult to find their sweet spot. So in ModelKeeper, we introduced 3 system components to tackle this challenge. First, model matcher identifies the similarity of 2 model architectures, and then select a model with high accuracy and similarity from the user-specified model zoom. Then, mapper transforms the weights of their parent model, even in the presence of different architectures. Zoom manager scales up the service to serve thousands of daily jobs and to register and evict Zoom models on the fly. Next, let's tackle the first challenge, how to identify the models with similar architectures to the query model. Here, a high similarity means a larger number of transformable weights. As the model is often a graph with potentially hundreds of tensors, we must quantify this number of transformable weights at the graph level. Now you might be wondering, why not just use the classic graph matching? Actually, these solutions are insufficient. First, we prefer to match the prefix of the graph because model computation is directed. Losing the weights of the prefix tensors can lead to cascading information loss to subsequent tensors. Also, matching can be partial. Thinking about we can transform a smaller weight matrix to a large matrix, or keep warming up some tensors, like tensor 4 in this example. Moreover, graph matching is NP hard. Existing solutions can hardly scale up to serve thousands of daily jobs for interactive service. So we introduced a structure-aware matching heuristic. Our heuristic follows dynamic programming to identify the maximum number of transformable weights between 2 model architectures. It starts in the topological order of tensors, matching from the prefix to the suffix. In this table, each cell records the best similarity achieved so far after matching all the prefix. So there are 3 possible operations when advancing to the next cell. See, we can match the current 2 tensors, or skip matching the current tensor of the parent model, or skip matching the current tensor of the query model. Here, we want to maximize the total number of transformable weights, so we can score each operation in terms of the percentage of the weights that we can transform in matching 2 tensors. But we need to penalize the skip parent operation because it loses the tensor weights of that parent model. Now, we enumerate these 3 operations and take the one that maximizes the similarity score. This way, when we move to the lower right corner of the table, we'll get the end-to-end model similarity. Now, models with high similarities have more transformable weights, but we also prefer a parent model with high accuracy at the same time for more beneficial weight transformation. To approximate this sweet spot, we introduce a bucketing design to quantize their frontiers. In this example, we allocate all models in the zoo into different buckets in terms of their similarity to the query model, from bucket 1 to bucket 5. Then we turn to the top similar bucket, say bucket 5, in which we select a model with the highest accuracy as the parent model. This way, we are using a parent model with high accuracy and similarity. Now, we are likely to select a model with similar architectures, but these 2 models can often have different architectures. To transform the information as much as possible, we take the concept of function-preserving network operators from machine learning theory, and then introduce 2 operators to reshape the tensor weights. In this example, the width operator will perform weighted replication to widen tensor 3. Then the depth operator will insert an identity tensor as tensor 4 to directly pass the output of tensor 1 to tensor 5 to preserve the same information. Finally, Mapper copies this transformed model weights to the query model, and training starts to search for better weight values from this initialization. So far, we have talked about how to efficiently warm up a single model. But the cloud model zoo can often have thousands of models. As we need to identify the similarity between the query model and models in the zoo, we must make this more scalable for interactive service. Intuitively, models with similar architectures would have close similarity to the query model, so we can cluster the model zoo into different groups in advance. Here, we cluster the model zoo using the k-methods technique and then introduce two-stage matching. This way, when the query model arrives, we'll first match it with the group centers and then the members of the top similar group, thus reducing the total number of matching operations needed to find similar models. Actually, our efficient matching heuristic and clustering make it possible to serve the user request in a few seconds, even for the practical scale of the model zoo with thousands of models. In our paper, we have more details to build ModelKeeper toward a practical service. For example, we discuss how to manage the model zoo subject to the storage capacity, because we may not have enough space to store all models in the zoo. And we also need to avoid low accuracy models in the zoo when running ModelKeeper in the world. To the best of our knowledge, ModelKeeper is the first automated training warm-up system at a cluster level. It can support many popular frameworks like the AutoML framework of Microsoft and Ray. We evaluate ModelKeeper using a cluster of 80 machines. The cluster runs thousands of jobs for more than a month. For each workload, ModelKeeper starts with an empty model zoo, and jobs will contribute their models to their zoo when training completes. In our evaluation, we care about the amount of training execution that we can save. And let's start with model architecture search task and compare with Retaileri and AutoKeras. These two frameworks rely on the lineage of model mutation during search to copy the tensor weights to the new model. The rightmost column reports the amount of training execution saved to get the same model accuracy. It's the average of all models training in that specific workload. We are seeing that using ModelKeeper to complement them can save the GPU hours by up to 75%. This directly leads to faster training completion, about 4 times faster, because we are doing less to get more now. Here, I want to note that these two frameworks are limited to the scope of model architecture search, because it's impractical to capture this lineage of different jobs and across developers. Instead, ModelKeeper can benefit various tasks, like ensemble learning. Here, we also set up a Ray cluster where tens of developers submit their training jobs to the cluster over time. And we are seeing that ModelKeeper can achieve large GPU saving for all these use cases. In our paper, we have more details to show that ModelKeeper achieves this benefit without hurting final model accuracy, and is able to warm up jobs across different data sets using different model zones. To recap, ModelKeeper is a training warm-up system that can automatically repurpose the weights of previously trained models. All code and benchmarks are available on GitHub. And that's all from me today about ModelKeeper, and I'm happy to take questions. Thank you.